In this section, we will introduce four common thermal processes. While a system can interact with its surroundings in many ways, the heat and work involved in these processes must always obey the first law of thermodynamics. In each case, the process is assumed to be quasi-static, which means that it occurs slowly enough that a uniform pressure and temperature exist throughout all regions of the system at all times. The first thermal process we want to discuss is an isobaric process. This is a thermal process that occurs at constant pressure. For example, consider a substance, a solid, liquid, or gas, that is contained in a chamber fitted with a frictionless piston. The pressure in the substance is applying a force to support the weight of the piston and a block that is resting on top of it. This determines the pressure, which remains constant throughout the process. Heating the substance causes it to expand and lift the piston. If the piston rises at constant speed, then the force on the piston is still equal to the weight of the piston and block, and the pressure in the substance remains constant. The substance does work in moving the piston and block through a vertical displacement. The work can be calculated using equation 6.1, where F is the magnitude of the force and S is the magnitude of the displacement. If the surface area of the piston is A, then the magnitude of the force is found using equation 10.19. With this substitution, the work is given by the following. In this expression, we have the product of A times S, which is just the change in volume of the substance delta V, which is equal to V final minus V initial, which are the final and initial volumes respectively. Thus, the relation for an isobaric process is the following. Notice that the relation is consistent with our sign conventions from our previous discussion of the first law. The work will be positive when it is done by the system, as it expands when heated. Note that V final will be greater than V initial in this case. However, if V final is less than V initial, then an isobaric compression takes place and the work is negative, which constitutes work done on the system in order to compress it. It is often convenient to display thermal processes graphically. For instance, the figure below shows a plot of the pressure versus volume for an isobaric expansion. Since the pressure is constant, the graph is a horizontal straight line, beginning at the initial volume V initial and finishing at the final volume V final. The work, which is P times V final minus V initial, is just equal to the area under the graph, which is shown by the shaded rectangle of height P and width V final minus V initial. The next thermal process we want to consider is an isochoric process. This is a thermal process that occurs at constant volume. This next figure illustrates an isochoric process in which a substance is heated. The substance would expand if it could, but the rigid container keeps the volume constant. Because the volume is constant, the pressure inside the container increases. Although enormous forces can be generated in the closed container, no work is done since the walls of the container do not move. Consistent with zero work being done, the area under the curve, which is just a vertical straight line, is zero. Since no work is done, the first law of thermodynamics shows that during an isochoric process, the heat serves only to change the internal energy of the system. A third thermal process that we will discuss in more detail in the next section is an isothermal process, or one that occurs at constant temperature. And finally, the last process we want to mention is an adiabatic process. This is one that occurs without the transfer of any heat. Since there is no transfer of heat, either from the system or to the system, Q is zero, and the first law indicates that delta U is equal to minus W. Thus, when work is done by a system adiabatically, W is positive, and the internal energy of the system decreases by exactly the same amount. Likewise, when the work is done on the system adiabatically, W is negative, and the internal energy increases correspondingly. As a final note in this section, we should mention that real processes may be complex, and that they don't exactly follow one of the four processes we have discussed above. For example, this figure shows a process for a gas in which the pressure, volume, and temperature are changed along the straight line from x to y. Using integral calculus, it is possible to show that the area under the pressure versus volume curve is equal to the work done for any kind of process. In the graph shown, the work done is depicted by the shaded region. Notice that the volume increases, so the work is done by the gas, and it is therefore positive by convention, as is the area. If in contrast, a process reduced the volume of the gas, then the work is done on the gas, and it would be negative.